Okay, so next up is Martin Lindquist from Johns Hopkins. He's going to give you the statistical angle.
Thank you. It's really heartening to see so many people come in and see a session on reproducible neuroimaging. And so just to start out, I'm going to give a little bit of glossary here. So people talk about replicability and reproducibility. So when they talk about reproducibility, when I talk about reproducibility, I mean that independent researchers reanalyze the same data set. So that's, and if they get the same results, then the results are reproducible. Replicability, a mouthful, it means that an independent researcher collects a new data set on the same topic, and you can reproduce, and the results are replicable. So that's the way I use it. Other people have different definitions, but that's just to set up the rest of my talk. So the ability to replicate results is really a cornerstone of all science. And if we can't replicate results, then anything that we do is just a set of unverified beliefs. And so there's recently been a bunch of different high-profile articles that have claimed that the lack of replicability is reaching sort of epidemic levels in all of science, but also in our field. And that's one of the reasons why having sessions like this is so important, to kind of make people think about things. And so in this talk, what I'm going to try to do is I'm going to try to focus on how the interplay between exploratory and confirmatory analysis influence the issue and this lack of I should have said reproducibility then. All right. So in general, in statistics, statisticians often make a distinction between exploratory data analysis, or EDA, and confirmatory data analysis, or CDA. And so EDA is used to summarize the main characteristics of the data, and it's often used using visual tools. This comes from Tukey in the 70s, saying that, well, when we have these new data sets, we have to figure out ways of exploring them and summarizing the information in simple, easy-to-understand methods. CDA, on the other hand, uses traditional statistical inference tools to quantify the extent to which deviations from the model can be expected to occur by chance. And so, informally, any method of studying the data set that doesn't include a formal statistical model kind of falls under the EDA umbrella. So whenever you have a formal statistical model, then we usually talk about it as being a confirmatory method. So again, EDA was developed to encourage statisticians to explore the data and formulate hypotheses that could lead to new experiments. Because if you just went into an experiment with a certain hypothesis and did a confirmatory analysis, you might miss all these interesting new things that you hadn't thought about. So EDA is really important to be able to look at the data, massage it, look at it from different angles that you're usually not used to, and try to figure out what's interesting about this data set that I can't see now. Now, the idea then was to use confirmatory methods to test these hypotheses and ultimately create new knowledge. So at the end of the day, we are scientists. We want to create new knowledge, right? So exploratory methods are very good to formulate hypotheses, but we need these confirmatory methods to verify them and test hypotheses. All right. So far, that's all well and good. And so what about our field, neuroimaging? Well, neuroimaging is a relatively young discipline, and our understanding of the brain, frankly, it's pretty rudimentary, right? It's a very complex organ, right? And so we have a relatively rudimentary understanding of what's going on. So therefore, just constraining research to only currently used strategy would really not be such a great idea. So the only thing you get to do is run a GLM, right? That would be a boring world, right? It's been a good workhorse, but if we just constrain to certain hypotheses, then really that's not a good idea. So there remains a strong need to kind of continue to develop new hypotheses and analytical approaches to move the field forward and create new knowledge. Okay? So the argument here is that data exploration is critical first step in knowledge creation, but in itself, it doesn't create the knowledge. So to obtain valid results that are reproducible or replicable, it's important to kind of balance the exploration with more confirmatory approaches. So we want to search the data and find interesting new angles to attack and understand what's going on in the brain, but we still need to be able to use these confirmatory approaches to sort of make a final assessment and increase our knowledge about how the brain works. And so this is all well and good, but this necessitates sort of a cycle between exploration, confirmation, and this is what's going to move the field forward. So this is critical, but it's hard. And it's often done poorly. And so it necessitates a very careful balancing act. And so what I'm going to try to do today is just sort of illustrate that, you know, it's important to balance exploration and confirmation, but if you do it wrong, then all bets are off. Okay? So again, EDA, you know, again, this is sort of just a way to get to know your data set. It consists of graphical summaries, various decomposition techniques, and things like that. And this is a wonderful way to examine the data. It's crucial for evaluating the validity of assumptions that we use in later models, and also to generate new hypotheses. So all these exploratory techniques can provide a really deep understanding of the underlying processes that give rise to the data, right? But by itself, EDA doesn't provide definitive answers, and all findings must be confirmed using new samples or independent data sets. Okay? So if you find something with exploratory data analysis, you need to get a new data set, and you need to confirm it on that. So here's some example of how we use EDA in our own work. So we often, when we get a new data set, we take the mean of the data, the standard deviation, we look at the global signal, we look at correlations between things, and this is really useful because it allows us to spot outliers, it allows us to spot things that are unusual about the data set. So this is a crucial part of quality control. So this is a way of exploring the data to make sure that it adheres to all the assumptions and whatnot that we believe that the data should adhere to. PCA, principal component analysis, another awesome way to explore your data set. So you take a principal component, it decomposes the data into components that explain most of the variance, covariance structure of the data, directions. And so here we can look at this and we can sort of explain, oh, look at these. There's interesting regions that seem to be covarying. That's really important. That's something that we should explore further, right? So this is a way of just, without any a priori knowledge, just going in and trying to figure out what's interesting in this data set. What can formulate new hypotheses for me? What can help me generate the next study? CDA, on the other hand, so the confirmatory data analysis, focuses on very specific questions, right? And these questions should ideally be hypothesized at the onset of the study. If they're not, you can run into trouble, and I'll illustrate this in a bit. And here we usually use probabilistic models. So probabilistic models, they're based on certain underlying assumptions, and they're formulated and used to test a certain hypotheses of interest about the data set. Okay? So in contrast to EDA, confirmatory analysis provides a legitimate basis for performing inference. And this is a critical part of knowledge creation, because we're hypothesizing that we're going to see effect. We create a model for it, and then we test it and hypothesize, and the inference says yay or nay, we can make this claim. That's important. You create knowledge that can be passed on in textbooks and whatnot. So what's an example here? Well, our good old friend, the GLM, if used correctly, is a good way to show that. So here I'm interested in, are there significant differences in activation in the DLPFC between two groups of subjects in a working memory task? Let's say I have normals or controls, schizophrenics or controls, and I want to see whether or not there is normals and okay. I want to see whether or not there's a difference between these two groups in this task. Well, I could set up a GLM in the following way. So this is sort of the I think this is, that's the first level model, right? Where I have all the subject specific here, and here's the second level model where I can estimate the amplitude for the two groups. And then doing this, I can now test the hypothesis, for example, that the difference between these two groups is bigger than 0 or something, or is equal to 0. That's my null hypothesis. My alternative might be that it's bigger than 0. So this is a stringent mathematical model kind of describing this. We can argue about whether this is the appropriate model or not, but this is a mathematical model. The key points here is that it takes into consideration the within subject variation. It takes into consideration the between subject variation. Because of this, the results will tend, if you fit this correctly and take into consideration all of these aspects, these results should be generalizable to a new sample of subjects, right? And that's critical. So we've modeled the noise, we've modeled the variation, we've taken that into consideration, and so we have a sample of subjects that we're studying, but because we've taken this between subject variation into consideration, it should be generalizable. And hopefully it should be reproducible. Now, all bets, this might not be the appropriate model and all these other things can happen, but in general, this is the appropriate way to do this. Now, EDA comes into this in the sense that we're assuming that the residuals in this case are normally distributed, right? And so how do we test that? Well, we can visualize it. We can do all types of things. We can use EDA. So our old friend exploratory data analysis comes back, and that's a useful use for motivating these models. So, all things are good here until people decide to conflate exploration and confirmation. So one of the great dangers in science is the practice of turning an exploratory analysis into a confirmatory one midstream, right? So as an example, let's consider the dishonest statistician. I have this new drug, and I really want to show that this new drug has a significant effect compared to a placebo. So what I'm going to do is I'm going to keep sampling subjects until I get a significant effect, and then I'm going to turn off the clinical trial. That doesn't sound so good, right? I mean, so that's a way of me snooping and looking at the data and sequentially adding subjects. So I'm sort of searching until I get a significant result. Now, none of you would do that, but that is sort of a nefarious thing where you're sort of conflating search and confirmation. So this is such a big thing that I could fill the whole page with synonyms of this. So it's called data dredging, data fishing, data snooping, p-hacking. I think that's the latest one. So this has so many names because it's unfortunately so commonplace, right? And so all these things are meant to cover unacknowledged exploratory data analysis with the sole purpose of finding a statistically significant result. So you explore the data and you try to find interesting things. And once you find something that's significant, you call off, you're like the dishonest statistician. You call off the search, right? But you not only do that, you only report the significant result, and you make it appear that was your primary hypothesis all along. I was always looking for that effect. That was at the beginning of the day. That was what I was interested in. Now, that's all well and good, but this is really exploration over a set of confirmatory analysis, and that's not going to be such a great idea, right? So this is probably not going to be very reproducible because of a lot of different things. So the problem is that the relationships may appear due to chance, and the strength of these estimates are likely going to be overestimated. So any inferential tests in this scenario are likely invalid, and the reported p-value will be grossly misleading and calling the significance into question. And so, of course, you will probably, no doubt, you might be able to get a paper out of it, but nobody's ever going to be able to replicate it, and you're actually sending science down the wrong path. That's too bad. So this all relates to the big kind of concerns that were a few years ago about selection bias. So this is sort of related to that. And so here the idea is that we search the brain for regions that are correlated with some behavioral task. And here we see that, well, geez, we have 20 subjects, and this is our threshold, so it's a stringent threshold. So we have contrast maps and behavioral scores for each subject, and then we basically look throughout the brain and try to find significant results, right? And so here, this is a typical significant voxel, has correlation of 0.8, and that's really great, and nature's calling, right? And so we're really excited about that, but it's sort of fake in this sense, because in searching for this significant test, we're conditioning on having a high observed effect size. So you actually have to have an effect size of above 0.67 to even be considered using this threshold. So if you were just by pure chance to get a significant result, it's going to be sky high and it's going to look really impressive, but it probably won't be replicable. So here's just a cartoon image of that. So basically, if you have a distribution of null correlations and of active correlations, if you threshold it, you're always going to get sort of an overestimated effect size and that you won't be able to repeat. So the noise is sort of helping you to get higher correlations. And I think that some other people are going to talk about that as we move along. So what's another thing? Well, this is a term. It's an old term, but I'm trying to brand a new term here. Pipeline fishing. That sounds like a good term here. So what's pipeline fishing? Well, I think this is going to fit well with what Steve Struthers' talk is going to be about, I think. Well, this is the practice of altering analysis strategies until you find a significant results. And this is another way of confounding exploration and confirmation. So I always do the same pre-processing pipeline, and lo and behold, I didn't get any significant results. What do? Well, I go back and I change the pre-processing pipeline. Oh, lo and behold, I get significant results. Well, now you're kind of searching, right? You're searching until you get something significant. I mean, it's human nature to kind of try to figure out and get something, but it's very dangerous. And there's a very nice paper, there's a series of papers by Karp, that actually show that there's more pre-processing pipelines than studies, right? So basically, there's so many individual pre-processing pipelines, and it's so unclear how they interact with each other. It's going to be so easy to sort of go through lots of different types of pre-processing pipelines and find one that fits your needs. And that's potentially very, very dangerous, okay? And so I think Stephen will talk about that a little bit. And so again, I believe that tailoring pipelines to obtain significant results is a serious problem. So here's an example of pipeline fishing. I fit every possible permutation of doing motion correction, just every kind of like hundreds of, thousands of different permutations. I get all my brain maps at the bottom, and I choose my favorite. And then I say, well, this is how I pre-process the data all along, and I got these beautiful results. Well, that's all well and good, but are you going to be able to reproduce that next time on a new data set? Probably not, right? Maybe. I mean, but it would be very, very hard to argue that you would. And so again, this is from the same Karp paper I mentioned before, where he looked at the spatial distribution of peak activation location across pipelines. So this is the same data set, same task. The only thing that was different was he made different pipeline choices. He made lots of different pipeline choices. He must have spent a lot of time doing all these things. But look at this, the maps, these spatial peaks are all over the map, right? It's just no rhyme or reason here. And so this is what I think could potentially be a very serious problem, because this is something that there's no really set pre-processing, and my goal is not to say that there should be one pre-processing stream, but the goal of what I'm trying to say here is that can confound your results. Okay. So what are some guidelines? Well, I would say that any novel effects that are suggested by exploratory data analysis should be validated by an independent confirmatory analysis before being treated as an established finding. So it's fine to search through your data and find interesting patterns. By all means, this is the fun part of data science, right? You want to go in and you want to find interesting stuff, right? But at the end of the day, anything interesting that you find, you have to verify later on. Central claims of a paper should be supported by a valid confirmatory analysis. So if my central claim is that this effect exists and there's a difference between these subjects, it should be done using a confirmatory analysis. But by all means, report any unconfirmed exploratory results, but let people know that they're unconfirmed exploratory results that should be confirmed later on. Okay? I think that's important. So I've talked about exploration and confirmation, but my title had two other words, model and algorithm, right? And so this sort of fits very nicely here, because one of the main differences between EDA and CDA is the presence of a model in the latter, right? So I made the point is like the GLM, we're modeling the within subject and the between subject variation. So we're taking into consideration the variation between subjects and whatnot. And so that's the crucial part in this, I believe. And so what is a model? Well, it's a mathematical description of a real world phenomenon. It's not perfect. No models are right, but some are useful, as famously said, and that's correct. But it uses probability theory to describe the parameters of an unknown distribution thought to be generating the data. It drives any inference, so we need it to perform inferential procedures, and it allows us to potentially generalize results and create new knowledge, which at the end of the day is what we want to do, because we're scientists. All right. So to date, the sort of the scientific method that most people work on has been built around formulating testable hypotheses using models. So you have this sort of hypothesize, model, test framework, right? And so experiments are used to confirm or falsify models, but according to some, in the big data era, this is kind of becoming obsolete as we're faced with massive amounts of data. So when we have massive amounts of data, models are sort of a little bit falling out of favor. And I think this is sort of a little bit dangerous. And so there's sort of kind of a growing trend to use algorithmic approaches and treat the data mechanism as unknown. Okay, so you're not really so interested in how the data was generated, but you have these algorithms which are sort of like step-by-step recipes of operations to solve a problem. So the idea is that, well, let's analyze the data without hypothesis and let these algorithms, these recipes, find patterns that science can't. And so the take-home point is that, well, if you just want to predict behavior from data, do we really need to understand why? If I have a model that allows me to predict behavior from the brain, who cares why? Right? If I have an algorithm, sorry. Well, for certain applications, that's fine. I write financial trading here. So if you're doing high-frequency financial trading, I want an algorithm that makes me as much money as possible. I don't really care why it's making me money. You know, I just want to make money, right? And so in that case, finding patterns may be more important than understanding them. And that's true of a lot of fields. So I'm not poo-pooing this, but there has to be sort of a time and a place for all these things. So the point I want to make here is science is not really solely about finding patterns. Rather, I think it's about finding explanations to patterns. So finding patterns is really important, right? But we also want to be able to explain why those patterns exist and why they work and things like that. And I think that's a critical thing that sometimes get lost in a lot of these algorithmic approaches. And there's plenty of good scientists that use these very well, but I think oftentimes it sort of gets lost in the shuffle. And that's what I'm a little worried about. So we seek to go beyond the range of the data. So again, sometimes if not used properly, these algorithmic-based approaches don't really tend to produce the necessary interpretable parsimonious descriptions of the phenomena that we're interested in. And there's sort of like an interesting thing. You can use Google searches to figure out where there's flu outbreaks, right? So if people are Googling Thermoflu or something like that, or the medications, they can say, well, there's an outbreak in Albuquerque or something like that. So Google has these awesome algorithms for finding that. But what does that teach us about the mechanistic understanding of flu trends? Not really much, right? So it has a time and a place, and it has an importance if you're interested in whether there's a flu outbreak in Albuquerque, but does it teach us anything about the science of flu trends? Probably not, right? So I think that's sort of an important thing to keep in mind. So that's my take-home point. Is I'm a fan of models, so I like models because it gives me a way of modeling things that I think are interesting in the data and explaining things. And so algorithms are great as well, but I think we're in the knowledge creation business, and we have to keep that in mind. So there's a great deal of pressure to find exciting new results in any given experiment. Why? Well, experiments are very expensive. Right? It costs a lot of money to sample even 20 subjects. And so when we have this data set, we want to make something out of it, right? We want a Nature paper. We want a science paper, Unfortunately, you find null results. Journals don't like to publish null results. Even though null results can be really important, journals don't like to publish them. And also, getting tenure is very nice. So, we want to have high-profile things. So there's a temptation to sort of, I found this interesting thing, so I want to just use pretend I did a confirmatory analysis. But, resist the temptation. Okay, so the take-home point is to ensure that results are valid and not deepen this replicability crisis. At that time, it's really important we take care not to sort of fish for results. So just keep your exploration separate from your confirmation. Understand your models, understand what's going on, and understand the patterns that you're seeing, and sort of be able to separate these things. And so I think we need to be very careful about making sure we understand what all these steps are. And so I'm really excited about seeing the talks for the rest of the day, where we understand how pre-processing and all these algorithms and whatnot impact the results and reproducibility. So with that, I would like to thank you.
Okay, so Martin's been a model speaker and finished a little bit early. So one quick question we have time for.
Don't you think that it's actually, I mean, lots of the exploratory analysis are more and more just moving into another pre-processing step? If you just consider ICA, it just splits up your data. Then, for example, you pick one network that you split from all of the data, and then you do a test on that. It's not that the ICA gave you the main result. It just split up the data from like noise to something else. But you use a certain network and then test it over the groups, for example.
Yeah, no. Again, there's some places where exploration, and so again, like one example was in the GLM analysis, using exploratory data analysis on the residuals to make sure that your assumptions were correct. That's perfectly valid. So there are cases where you can do that, but there are plenty of cases where it gets very hairy. So you really need to keep it very clean and try to realize when you're conflating these things. But absolutely, there are plenty of times where you get this interaction, which is seamless and important, for sure.
Okay.